So looking at number 12, this one is, if you remember, the last thing we learned was the little formula that looks like this. Okay? Huh? It was also, you are also going to use it in the lab. But the last two questions that we kind of worked on were based off of molecular weight. That's what the MW is. Density is the D. So you can do mass over volume for that as well. And then everything else is coming from your ideal gas law. Okay? So keep that in mind when we go to look at this. Okay? This says a compound has the empirical formula CHCl, a 256 milliliter flask at 373 Kelvin and 750 torr contains 0.80 grams of gaseous compound. Give the molecular formula. So, who can tell me the very last step of this problem? That would be the answer, but what's the last step? Multiplying by the mass ratio. Yeah, great job. Nice work. All right, cool. So, who remembers how to do that? What information do we need? You need molecular weight, so we're going to need your molecular formula mass divided by the who mass. Yes, your empirical formula mass. Awesome. All right, and that's going to give you a ratio that you're going to multiply by your empirical formula. Oops, I guess I can go around the whole thing. All right, so that's our very, very last step. So what do we need to get? Because we have empirical formula mass, technically. They gave us the empirical formula. All we got to do is add them all up, right? So who do we have to find? Your molecular formula mass, right? Okay, and so what we're actually solving for is molecular weight. So what do you think we're going to do? Yep, so don't forget this, your little formula that we were working on a couple days ago, or last week. And looking here, did they give us a pressure? Yes. Did they give us a temperature? Do we know what constant we're going to use? Which one? No, this one's in torr. So unless you convert. If you're going to change it to ATM, by all means do it. Otherwise, 62.4, right? Okay, yeah, okay. I was looking at the pretty P one earlier. All right, so 62.36. Okay? Oh, my gosh. That's upside down. All right, so 62.36, and that's all due to us having torr. Like I said, though, a lot of people were shouting out the 0.0821. That's fine if you convert it, okay? I just don't feel like converting it, so I'm just going to use the other R. And then finally, density. Do they give us density? Not directly, right? But we can get it from doing mass over volume, right? So with that mass and volume, just real quick, is milliliters going to be allowed for this one? Yes. It is not. So look at your R, and you tell me why it's not. Because it's all in liters, exactly. So we got to make sure we have it in liters ready to go, okay? So when we go to plug everything in here, okay, we're going to have our molecular weight. Actually, let me move this up just a little bit. Okay, we're going to have our molecular weight is equal to mass, which was 0.80. I'm just going MRT, by the way. So M times R, 62.36, times my temperature of 373 Kelvin, all divided by my volume, which we know we have to be in liters, times the pressure of 750. All right, so this is what you're kind of typing in. So go ahead and get that typed in. And once you've got it, let me know. What'd you guys get? Should be 90 something. Okay, 96.92 grams. Okay, so now I have my molecular formula mass. We're going to take that and we're going to say the molecular weight divided by our empirical formula mass. Okay, so we have 96.92 on top, all divided by, how do we come up with empirical formula mass? Correct. Good. We're going to add up all the elements from our empirical formula. So CHCl, and that comes out to be, don't round on this one. We'll go to 2 decimal places total, but don't approximate it. It's 28. Is that what you said? Oh, yeah. What is it? 48 point. Sorry. Okay, so when you divide that, you can kind of look at it and approximate it. What's it coming out to be about? 2. Okay, so we're going to take 2 times our empirical formula, and so your answer comes out to be C2H2Cl2, and there's your answer. Okay, so kind of cool. Don't forget the few formulas that you are kind of asked to memorize, which is obviously the dirt over P one is not on your guys' formula chart. Okay, it's basically replacing a bunch of things from your ideal gas law. So so don't forget about that. Also, don't get stuck. Don't just stop. Just think about it. Sometimes this approach helps is when you think about what is the last step that you're going to have to do in order to get this. So like if it was a perfect problem, what would you do? And usually you can find from there what information you actually do have, okay? And it's not so scary. All right, so go ahead and look at the next one. Our next one is gas stoichiometry, or it's titled gas stoichiometry. So you did learn this Chem 1 year. This was the one, these were the examples that we said sometimes you have to stoich it out before you can do your ideal gas law. Or sometimes you do your ideal gas law and then stoich it out. Right? So this was that 2-stepper one. So looking here, we got hydrogen can be prepared by passing steam through a hollow air tube which has been heated to high temperature. Then they give you the reaction. Calculate the volume of hydrogen formed at 0.98 atm and a temperature of 450 degrees Celsius, 98.3 grams of H2O are passed through an iron tube. Okay? So what's one thing that stands out to you right away? Celsius, exactly. So let's go ahead and fix that guy. Excuse me. Is it 723? Yes. I believe. Okay. All right, cool. Okay, so looking here, we want to calculate volume. We're starting from mass, right? Which one do we start with, do you think? Stoichiometry, or do we start with ideal gas law? This one we're going to start with stoichiometry, right? Going from mass. So real quick, what's the bridge between these two? Out of, thinking of the different possibilities that you can do when you're doing stoichiometry, what's the bridge? The mole, okay? So you are either calculating your mole from this guy with a lot of information, okay, and then going into stoichiometry to get grams or whatever they're asking for, or you're going to use your grams that they're giving you, calculate that mole, so now you have that last piece of information to solve for something like volume. That's the big picture of these, okay? And so, like you guys already told me, though, we're going to start with some stoichiometry, so let's go ahead and get that going. You guys can work at your own pace if you already know what you're doing. So we're going to have 98.3 grams of water, and we want to get to something about H2. So I'm going to go to moles of H2. I'm going to bring words down to the right, change into the mole of H2O. Ooh, that's a little off. And then we're going to go words down to the right, cross the mole bridge, or use my mole ratio from the balanced equation between water and hydrogen. Okay, so here I've got 1 mole of water is about 18.0 grams. And in the balanced equation, remember this part comes from your coefficients. So here I have a 4 in front of my H2O. Here I have a 4 in front of my H2. So it's a 4 to 4 or a 1 to 1, which is really nice. Okay. On a multiple choice, you can shorten this up, by the way. Once you see that it's the same thing, you don't have to do all this. Okay. Start working towards that. So when I plug that in, I am getting 5.46 moles of H2. Okay, so now I have the N for PV equals nRT. So my final steps are going to be plugging into my ideal gas law. Okay, I'm going to use the information from the problem. So they gave us 0.98 ATM times mystery volume, so that's who I'm solving for. We have 5.46 moles times, do you guys know what R to use for this one? 0.0821, and who is it based off of? ATM, pressure, good, okay. All right, so times that, and then, and by the way, if you've already forgotten, those little R values, they're all found in the yellow periodic table. They're on the inside, okay? So we're not just pulling those out of nowhere. We're going to 2 sig figs, I believe, on this one.
I'm going to use this for the AP exam, right?
Yes.
We're going to have
The R values are all there. Yes, 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 yes. Okay, and then, sorry, lost track. Oh, 723. Okay, and remember we want our answer in 2 sig figs. If you look in the problem, that was the smallest amount of sig figs in there. Okay, and since it's all multiplication division. So once you've got it, go ahead and shout it out, and we'll get it written down. 330 liters. There we go. Good. Awesome. Okay, so not too bad. Shouldn't feel too uncomfortable. Okay, just remember, your bridge is the mole. Always is. Okay? All right. Okay, so go ahead and look at the kinetic theory right there on the left-hand side of your page. Okay? And on here, you guys have heard of this. Okay? This is the KMT thing. I think that's what I usually call it. But KMT. So kinetic should be telling you that it's talking about your particles in motion. Okay? Or moving around. And all of your gas laws are basically referring to this theory because this theory sort of describes your ideal gases, okay? So your gases consist of tiny microscopic or submicroscopic molecules which are in continuous random motion, so that makes sense. That's the kinetic part. Number 2, the distance between molecules is large compared with the size of the molecules themselves. So the volume occupied by a gas consists mostly of empty space. Okay, now, question. Is this talking about ideal gases or real gases? On number 2, for sure. Like, do you feel like that's a true statement all around no matter what? Yes. What about when you have something like radon? Didn't it just get a little bit bigger? Or when you have like a huge molecule, didn't it get a little bit bigger? Okay, so this one's talking about ideal gases, big time. Okay, so we're gonna see, hopefully by the end of this lecture, I'm hoping we'll get to van der Waals, and that's gonna be a correction factor. And one of the things is that you gotta consider that's not always completely, totally true if things are close together. Then it starts mattering that they're taking up so much space. Okay, but in these large amounts of volume or this big open space, who cares? It's very negligible. Okay, all right. Number 3, gas molecules have no attraction for one another. True or false? In all situations. What do you guys think? Okay, so when you learned about intermolecular forces, you guys learned about polarizability. Do you You guys remember that? That was the little fluffy cloud, okay, of the electrons. And so when they kind of start hitting each other, all of them go like this, right? And now all of a sudden you have a polar molecule, even though it was nonpolar, right? So something like iodine, or I'm sorry, that's a horrible example, chlorine, right? Cl2, okay? And it has all these extra electrons, and it all of a sudden became polar for that instant. Now, isn't it going to be attracted to another I2 who's also polar? Do you guys know what I'm saying right now? When I say polar, that's when you have positive and negative sides, right? Okay, so is there attraction for gas molecules once in a while? Yes. Absolutely. So once again, this one is also talking about ideal gases, all right? So this is the whole fake thing that we were kind of stressing on that first day. All right, number 4, gas molecules move in straight lines in all directions, colliding frequently with one another and with the walls of the container. What is this describing right here? Pressure, good. 5, no energy is lost by the collision of a gas molecule with another gas molecule or with the walls of the container. All of them are perfectly elastic. So my physics people. Huh? Right. Yeah, it's not totally true. You're right. But I was going to say, just to help our juniors out, what did you guys learn perfectly elastic is kind of like? What was the example he probably used? Yeah, like a visual of a perfectly elastic collision. He didn't do that one? All right, so number 6 says that the average kinetic energy for molecules is the same for all gases at the same temperature. All right, so average kinetic energy, same at same temperature. And its value is directly proportional to the absolute temperature. Okay, real quick. When you learned in Chem 1 year, what did we tell you? We said temperature shows you the what of your molecules? The speed, right? Is that what this statement is actually saying? No, it is talking about only the kinetic energy. So today when we look at Graham's law, we're going to see that velocity doesn't necessarily mean temperature, okay? However, you can say that your velocity is proportional to that, okay? And your temperature is proportional to your kinetic energy. But obviously, everything has different masses, okay? So we can't always assume the same speed at the same temperature, just kinetic energy. All right. Now, gases are most ideal at high temperatures and low pressure. Why at high temperatures? What does that mean? Things are moving quickly, okay? And low pressure means you have lots of what? Space, exactly, all right? So that's where your gases are most ideal. The opposites of those is where they start acting like real gases, okay? Or they start acting like, they start having those attractions between things. Their volumes are going to start mattering, okay? So keep that little thing in mind right there. All right, if I'm not mistaken, you guys have a little space right there above the next little portion? Yes. Do you guys still have a little bit of empty space there? Yes. Okay, if you do not, you can flip it over to the back. You have a lot of empty space underneath the chart, okay? But I have one quick question for you guys to answer, okay? And this is kind of like a typical AP question. There it is. Okay, that's what I wanted. And so you don't have to write the question if you don't want. You just need the answer. But I want you to explain in terms of the postulates for the kinetic molecular theory, so all those things that we just went over, I want you to explain to me why pressure increases as temperature increases. Okay? So I want you to come up with, yes, you did. You actually did. So I want you to come up with your best AP response. Try and get all your points there, okay? But go ahead and write your answer. I'm going to give you guys about a minute and a half, 2 minutes, and then we'll talk about it. Okay, so this is talking about now that speed factor. Okay, so this is going to lead into Graham's law, all right? And there's a chance I'm gonna add this question to your post-lab questions after your lab because it has to do with effusion and diffusion. So real quick, before I go over the math part, what is diffusion? What does that word mean? Yes, everybody goes. Everybody does that. It's awesome. Yes, it means that I could have an air freshener in over here and it diffuses, it mixes throughout the rest of the room, right? It spreads, fills its container. That's what a gas does. All right. And so effusion. Who remembers what that one was? So effusion is the one where if you give it a tiny opening, it's going to go through there. Okay? So if you poke the hole in a cap, it's going to effuse out of there. All right? So that's what that word is. So in your guys' lab for the Dumas method, you guys are going to poke a little hole in your aluminum foil, and it's going to be coming out of the little hole. Okay? And so that's what we're talking about there. And so when we're saying the speed of these things, they're not going to all come out at the same time. We're going to hope, what do you think, the lighter or the heavier gases are going to be coming out first? The lighter gases, exactly, okay? And we're going to kind of rely on that, especially in your lab. So, so looking here, there is a beautiful, if you are a derivation person, I kind of am, I won't lie to you. But we are not going to do this in class because I looked it up. But in your book, if you want to look up this derivation as to why you have this little 3/2 thing, this is the average kinetic energy for ideal gases. So this is specific to gases. This is on page 218. In your textbook. So if you are a derivation person, please look there, okay? Because, yeah, it's going to help you understand where that number came from. It has to do with the fact that these things are colliding in this direction, and this direction, and this direction, okay? So 3 axes. And so that's where the 3 part is coming from. Otherwise, it's just kind of mixing together your ideal gas law with your kinetic energy idea, okay?
Is it 18 in our textbook? Or
in your textbook, okay? And it even comes with pictures.
Oh, nice.
Yeah. Okay. So it is a good derivation. It's pretty clear, but it's very long. So, but anyway, so that's very specific to that. Please look at your periodic table. That equation is not given to you. It's something they expect you to know. Okay. Fun stuff. So we'll start making flashcards, and we'll have all those things. We'll put them up on the walls for now, and then we'll start memorizing what we need to memorize. Okay. But what you need to take from this little page right here is this formula over here, okay, which came from setting gas law to what the kinetic energy formula is, okay? You could actually do that derivation yourself. It's very easy. You're just moving things over, okay? But what this is, this little RMS thing, it stands for root mean square. So that's a fancy way of saying that this whole thing is actually square rooted. Don't ask me. Don't know. Okay, because it's not what the formula is. But now I'm telling you, so you know what it is. Okay? And then, basically this little URMS thing, you could replace with the word rate. Yes, I know. It's frustrating. Just do it.
So they just had to make it more complicated.
It goes with the derivation. If you look at it, I understand why they did. It's just, yeah. Anyway, this is easier to understand. Makes it a little bit nicer to your eyes, okay? So it's the rate is the square root of this 3RT over, okay, this mm. What is mm? Molar mass. This is the kicker. Because we are now dealing with things like energy, okay, we got to be in kilograms. So you got to kind of go to what you probably dealt with in physics, okay, which is your SI unit for that. So kilograms means that you move decimal over 3 to the left, okay? It's dividing it by 1,000. All right. The other thing I want to point out, is this, because this is easily missed on this little formula down here. So what this is actually Graham's law down here, okay? And so what it's telling you is if you have to compare your two rates, if you have a ratio of your rates, you can figure out mystery molar masses. However, what do you guys notice about this compared to this? What did they do? They flipped it. And it has to do with this little step right here. Okay? If you divide things, you flip them over, and then, you continue on and stuff. So that's where it's coming from, but just please know that it is R1 over R2 is equal to the square root of MM2 over MM1. Okay? So I pointed out everything that you could possibly miss in these equations. Are we all clear? Okay, flip the page. Real quick. Is you guys are going to have a little liquid in your flask, okay? And it's not going to be very much. It's just barely going to be there, okay? And then you guys are going to seal this off with some aluminum foil, okay? And we're going to have it in a nice little beaker of boiling water. So that boiling water is going to cause that liquid, this volatile liquid, to turn into gas, right? And it's going to effuse out of a little hole, okay? And you guys are measuring mass before, mass after. This is called the Dumas Method. And Dumas, please say Dumas. It's actually pretty good. It's not the other method. But you guys are going to be using your dirt over P formula for this. And you're going to find the molecular weight of that volatile liquid, okay? So obviously you can see that volume will stay constant, mass is going to be the thing that changes, and yeah, okay? Now, is it super related to Graham's law? Not really. I'm gonna throw one calculation in there so you guys can solve for it and get the hang of it, but that'll be it, okay? But this is where I am going to kind of stop, okay? So make sure your pre-lab is all done. You guys have 2 minutes to knock it out if you haven't done it yet, okay? It's really not, it's not horrible, I promise. All right. Calculate, stay positive. All right, calculate the average velocity of a sample. Oh, goodness gracious, did I go over the big idea of Graham's law? No. Okay, just write it at the top right here, okay? So the whole idea of Graham's law, and my people who are in physics, you should recognize this. Okay, right? And we know that, how are these two things related? Inversely or directly? Inversely. If we're keeping kinetic energy constant, if I decrease mass, my velocity goes up. Smaller things go faster. Bigger things go slower. That right there, okay, that's what Graham's law is all about conceptually. Okay, it's about the inverse relationship between mass and velocity. Okay, because what we're assuming with gas laws is they are at the same temperature. They're in the same container, same situation. However, we got two different chemicals. They're not going to be going the same speed. Okay, it depends on their mass. Okay, cool? Cool, awesome. All right, so calculate the average velocity of a sample of helium atoms at 25 degrees Celsius. So first, let's take care of this business. What is that? $298. By the way, that one start getting in your head to memorize. It's a little bit easier. $298. That's room temperature. Okay? Okay. All right. So we got 298K. So we want the average velocity. We want the rate. So without flipping your page over, I want you to try and remember it. This is that URMS looking thing. That is now what we're going to call this formula. I love it because it is. It is a mess of a formula. I love it. You are a mess. Oh my god. Okay. All right. So what is it? Let's see if we got it.
Something over molar mass.
Root means square. So we need the square root first. Remember, it was based off of the 3/2 RT, and it was also the 1/2 MV squared. So it is 3 RT over molar mass. There we go. Okay.
Did you get to memorize these?
Unfortunately, they're not on here.
Why? Is it on the test?
Yes, and it's because it comes from a derivation. So if I can find an easier way for you guys to remember, I'll look it up. Okay. So I'm gonna do my homework and see if there's a better way. Yeah, but we need to know how to memorize this part. Because they're not asking for this part. I agree. Just tell the AP people, you are a mess. All right. Anyway, so this is your, so this is what we're doing. Okay. So we're going to go ahead and start plugging in. We got square root 3. All right. Does it matter which R we pick? No, not really. So let's go ahead and go with 0.0821. Okay, be careful on this one. What does the molar mass have to be in? Kilograms per mole. So we're going to say if helium is 4 grams, it is 0.004 kilograms. Go ahead and type that in. Let's see what we get. And your answer needs to, unfortunately, go to 2 sig figs. So tell me what the actual answer is first, and then we'll change it to 2 sig figs after. You guys haven't even seen the van der Waals equation yet. That one you don't have to actually calculate. It's on your paper. Huh? Yeah, what did you get?
I got 18,000.
No, not that big.
Okay.
What did you get?
Oh, I know what I did wrong. Okay.
What?
10.
I got 135.436.
You're closer, but no. Okay, so the thing that we do need to change on this is this number right here. We have to use the one that's related to energy, which is the 8.31. And now you guys will for sure get it. No. Yes, you should still get over 1,000. So you should have gotten 1,362-ish?
Yes.
Okay, so 2 sig figs, how do we take care of that?
1,400.
1,400, so 1,400. All right, what are my units for velocity? Meters per, not squared, meters per second. There we go. Good. Okay. All right, cool. So my bad on that, but good catch. Nice work. So big thing for these is since we're talking about energy, we do have to use the one with joules. Okay? Are we all clear? Sweet. Okay, so you guys actually still have a little bit of time, so I'm gonna push y'all, okay? Go to the next one. The next one's actually easier, I promise. Look at the next one. It's easy. It'll make you feel good about life again. All right. No, it is not the same formula. All right, so this one is I'm gonna use Graham's law. Okay, so this one says oxygen O2 diffuses at a rate which is 2.23 times faster than a sample of a reddish brown gas. Determine your molar mass of the unknown gas. So this is one where we are finding MM2. Okay, they gave us a what? If you say something is 2.23 times faster, that's a ratio, right? You guys see that? So this is like me going the rate 1 over rate 2 is equal to my square root of mm2 over mm1. That's Graham's law right there. So when they only give you the ratio, you set 1 to be 1, right? You guys see that? It's a 2.23 to 1 ratio. So you're going to say 2.23 over 1 is equal to square root. So the only thing you can screw up on this one is the algebra part, okay? You know that O2 has a molar mass of what? 32. Okay. And we are looking for that one. So what's the first thing you do to get rid of a square root? Square it, right. So we're going to square both sides and also get rid of that nasty fraction because who cares? Huh? Sorry. Did you guys hear that? Change it to kilograms. This will probably be where we stop because obviously Miss Fogel keeps making little stupid mistakes. All right, there we go. Okay, so 2.23 squared. Right. So I'm going to go to 2 decimals, is equal to molar mass over 0.032. So now we just multiply by the bottom guy. And we get an answer of 0.159, which is 159 grams per mole.